Let's start section 3.4, Carnot efficiency for heat engines. Steam engines, gas turbines, and internal combustion engines are examples of machines that convert heat into useful work. But what we are interested in here is how efficiently can they do. Efficiency is a very important subject in power generation. This slide lists a number of technical terms that for you to help you to understand the content easily. Section 3.4.1, heat engines. Let's first understand the heat engine. The workflow of a heat engine is that the engine will extract heat QH from a high temperature source and convert part of the heat into work, and then reject the remaining heat QC into a low temperature sink. The high temperature source could be a boiler, and then this is the heat engine is usually in the form of rotating shaft, and we usually use this one to transform the mechanical power into the electricity. And the remaining, the low temperature sink is usually either an atmosphere or a local body of water. So that is the workflow of the heat engine. And we use this example to try to investigate the maximum efficiency of heat engine. The thermal efficiency of a heat engine is the ratio of work done to input energy provided by the high temperature source. So the thermal efficiency is equal to the net work output, which is W, divided by total heat input, which is the high temperature from the high temperature source, the heat from the high temperature source, QH. Since energy is conserved, which means the heat from the high temperature resources should be equal to the net work output plus the heat remained in the low temperature sink. Therefore, the thermal efficiency will be equal to QH minus QC divided by QH is equal to 1 minus QC divided by QH. Now let's understand the concept of this entropy. Entropy is a measure of molecular disorder or molecular randomness. The entropy scale is a pure crystalline substance at absolute zero temperature. Since at that time, every atom is locked into a predictable place in a perfect order. So at that time, the entropy is defined to be zero. The substance in the solid phase have a more ordered molecules, and hence it has a lower entropy than any liquid or gaseous substance. Entropy is not conserved in a process. This is very important. The heat and work is remained consistent during the entire process, but the entropy is not. In an isolated system in which the total energy cannot change, the only process that can occur simultaneously at once that results in an increase in the entropy of the system. So this means that for any process, this implies any process that can only occur when the entropy of the entire system increase. So the heat will always flow naturally from warm objects to the cold ones, but never will not be other way around, which means the heat will never flow from cold ones to the warm ones. Now let's back to the heat engine. How are we going to study or investigate the maximum efficiency of the heat engine? If an amount of heat Q is removed from a large thermal reservoir at a temperature T, the loss of entropy S from the reservoir is defined as a delta S is equal to the Q divided by T. Q is the heat from the thermal reservoir, and the T is the temperature. T is an absolute temperature, measured either using the Kelvin or Rankine scale. The following two equations shows the conversion from Celsius to Kelvin and from Fahrenheit to Rankine. So the Celsius degree plus 273.15 will convert into the degree in Kelvin, and the Fahrenheit plus 459.67 will convert into the degree in Rankine. As we learned from the entropy concept, the entropy must increase during the entire process. So the entropy added to the low temperature sink must exist the entropy removed from the high temperature reservoir, which means the heat at the low temperature sink divided by the temperature of the low temperature sink which is the entropy added to the low temperature sink will be above or more than the heat at the high temperature resource QH divided by the temperature at the high temperature resource TH. Therefore, QC, since TC and TH are the positive value, so QC divided by the QH will be above TC divided by TH. Remember, the heat engine thermal efficiency is equal to 1 minus QC divided by QH. Since QC divided by QH is more than TC divided by TH, therefore this value will be less than 1 minus TC divided by TH. So the maximum possible efficiency of a heat engine will be equal to 1 minus Tc divided by Th. Tc is the temperature at the low temperature reservoir, and the Th is the temperature from the high temperature reservoir. What this equation implies? This equation means the maximum possible heat engine efficiency increases as the temperature of the hot reservoir increase, or the temperature of the cold reservoir decrease. So which means if the difference between the hot temperature and the low temperature, the difference between those two is the maximum. The heat engine efficiency will reach the maximum value. In fact, since neither infinitely high temperature nor absolute zero temperature are possible, so we can conclude that no real engine can convert thermal energy into mechanical energy with 100% efficiency, which means the theta max will never reach 100%. This means that there always been wasted heat rejected into the environment or rejected into the cold reservoir. Usually, this heat, as we can know from the previous sections, the thermal efficiency of heat engine is usually less than 40%. So actually, this entire electricity generation process has a very low efficiency. That is the reason why the efficiency has become an important subject into the power generation. We will always try to increase efficiency. Now let's see this example. Consider a 40% efficiency heat engine operating between a large high-temperature reservoir at 1000 Kelvin and a large cold reservoir 300 Kelvin. Now question 1. If it withdraws 1 million joules per second from the high-temperature reservoir, what would be the rate of loss entropy from that reservoir? And what would be the rate of gain by the low-temperature reservoir? The second question is express the work done by the engine in volts. The third question is what would be the total entropy gain of the system? Now first, we remember the loss of entropy from the high temperature source would be the delta S loss. It would be the heat at the high temperature reservoir divided by the temperature TH, which is equal to 1 million joule per second divided by 1000 Kelvin, which is equal to 1000 joule per second. So this is the loss of the entropy from the hot reservoir. Now the gain of the entropy by the low temperature reservoir will be equal to the QC divided by TC. Since 40% of the efficiency so being used to the work, therefore the QC will be 0.6 multiplied times 6. The heat transferred to the low temperature reservoir is 0.6 multiplied times 6. The TC, the low temperature, the temperature at the low temperature reservoir is 300 K. So the QC divided by TC is equal to 2000 joule per second Kelvin. So the entropy gained by the low temperature sink is 2000. The heat engine converts 40% of its input energy into work. So the work is 40%, is 0.4 multiplied 10, 6. sorry, this should be times 6, exponential 6, and multiply, since 1 volt is equal to 1 joules per second, so that is equal to 400 kilovolts. Since there is no entropy associated with the work done by the heat engine, therefore the total entropy change is equal to the loss from the source plus the gain into the sink. So minus 1000 plus 2000 plus 0 will be equal to 1000 joules per second Kelvin. So the total entropy gained during this process is 1000. Now, this completes section 3.4.